Hello, good evening. First, uh, let me share my presentation. Is it visible to you? So there are very less people here as I can see it. Like it will be, and in fact, it's an interaction class. It will be helpful if you are a little interactive. Okay. Hmm. All right. Mm, So my name is Debmallo and I am your TF for this live session. Here we will be discussing the assignment zero that has been given to you. So I want to know where are like you in the course? What is currently going on in this course?
Maybe, sir, already lectures up till week 3 are released.
Okay, so week three are released. These live sessions are lagging behind basically. Okay, not an issue, but okay. I would also like to know, what are you doing currently? Like, are you an undergraduate student or postgraduate or doing something else? So,
I've done my graduation. I'm just doing this course for as an extra
okay, mm,
learning. Or something.
okay, all right, that's good. So, we'll start with this assignment zero's first question. So, here what they have asked is, I guess you have already submitted this assignment. So, can you like tell me what how have you approached this problem?
Sir, this question was like pressure. We know that the formula is
Mhm.
force upon area.
Yeah.
Then we can simplify it into dimensions
Mm-hmm.
respective terms. So for F, it's ml minus. So for F is mass into acceleration. So
Yeah.
mlt equals 2.
Yeah.
For area, we have L square.
Mhm. So this is for what you put for your force, and uh, for area you will put this. So you will get this as the correct answer, right? Hmm. So this is very straightforward. You just have to do the dimension analysis. So as you have already done this question, can you do the same for, let's say, some other parameter, for example, density, which will also be pretty easy. So can you tell me what this will be?
Yes, sir. So density will be ml minus cube because we have mass by volume, so
Hmm.
minus cube.
Yeah. So ml minus 3, right? Okay. You have already come across viscosity as well in your lectures, I guess.
Yes, sir. Yes, sir.
So, uh,
So
yeah.
for viscosity, we
Mm.
have the formula Newtonian law of viscosity tau is equals to
Mm.
mu d into dy.
Mm. Mm-hmm.
And if we talk about the SI unit, it's Pascal second. So Pascal is for
Mm.
pressure.
Yes.
So out
Mm.
of pressure, we can say that ml minus 1 and
Mm.
T minus 2, and there is also second, so ml minus
Yes.
1, T minus 1.
Yes, that's correct. Is this dynamic viscosity or kinematic viscosity?
So this is dynamic viscosity.
That's correct. Okay. All right. So we will move to the next question. So here the solution is there. Hmm. So okay, let's follow the same drill. How have you approached uh, this question?
So these questions I don't find these are related to this because
Mm-hmm.
they're related to matrix and I don't remember the concepts now.
Okay. So these are actually quite, you will find that they will be relevant at some point of the course. So since
Okay.
in fluid mechanics we deal quite a lot with tensors, especially second order tensors. And second order tensors, when they are broken down in components, it's very easy to represent them in forms of matrices, right? Hmm.
Okay, sir.
Here, in actually the next few questions, we will be uh, solving some very basic questions of matrices. So here they want to know what is the rank of the matrix. Hmm. So uh, can you tell me what do you understand by a rank of a matrix?
If I'm not wrong, I think that's the
Hmm.
higher order, highest order non-vanishing minor, if we can say.
Yes, sure. And like in more simpler terms, so for example, if I say this is a three cross three matrix, and suppose if I say the rank of it is two. Hmm. So whenever we are like talking about a second order matrix like this, means this is generally used for solving like linear equations or like
Yes,
a
yes.
matrix is used for vector transformations, right? Suppose you have a vector x and you want to transform it to some vector y. Hmm. So what you can use is you can use a mm, you can use this second order tensor, which when broken into components will be represented by matrix. So it will be represented something like this. Hmm. And this will be basically you will have the three cross three matrix here. Hmm. And you may have a vector here, 3 plus 1, which will transform and to produce another vector here as 3 plus 1. Hmm. So what you are doing is you are solving for solving three equations, right? Three linear equations, like and finding out these values. Hmm. So this basically rank of the matrix is, basically says that how many of these rows are independent of each other. So when you solve these equations, how many of these rows, how many independent equations will you will actually get? Hmm. So if the rank is two, that means one of these rows can be actually uh, attained by performing linear operations on the other rows. Hmm. So how do you go about finding this rank of this matrix? So mm, can you describe the process of finding out this rank of a matrix? Anyone can say.
Maybe like we can take the like determinant of this whole matrix and check
Mhm.
whether it is equal to zero or not.
Yes,
So
sure. That will give you an idea that
that
the rank is
matrix
three
is
or
equal to
not.
three or less than three, I think.
But it can be one as well. It can be two as well. So how do you exactly calculate the rank? So we will.
number of
Yes, please.
number of non-zero rows after row and column transformation.
Mm. Okay. Will we do both row and column transformation or any one of them?
Anyone?
Yes. So we can do row transformations on this matrix, and we
We can
can,
convert actually
mm,
this into row echelon form.
yeah, we can convert this into row echelon form. What is row echelon form? Row echelon form will look like this, where this. So this below the bottom below the diagonal, all these elements, if these are zero. So all of these elements are 0, and we have, including the diagonal and the upper triangle, uh, we may have 0 or non-zero elements. All the non-zero or 0 elements will be here, and in the lower side of the diagonal, all elements must be 0. So this we can uh, attain this form by performing row operations. Hmm. So what are the row operations? We have three rules for these row operations. Hmm. So, for example, if you take any one of these row, by what do I mean by row? Like this is, for example, one row. So this row, what I can do is transform this row into some any scalar. For example, if I perform a row operation and this a is equal to 2, so if I multiply this whole row by 2, then it will be a row operation, and uh, we, we would perform a row operation, and this new second row will be minus 2, minus 2, minus 2. So that is one possible uh, operation that we can do. Another operation which is more you will be using the most is we can multiply a scalar to some other row and add it to this row. So this we will do for making these elements 0. We need to make the uh, lower triangle 0. So all the elements must be 0. For that, we will be using this second operation the most, to convert all these elements to 0. And the third operation that we can also perform, which is allowed, is we can exchange any two rows. Hmm. So all these three operations are basically allowed because they are the standard operations that we can do if we want to solve linear equations. So rank of this matrix will not get changed because what we are doing in using these operations is basically solving this set of linear equations. So we will see what we can do for this particular problem. So we have taken this and performed a row operation where the second row is taken and minus 4 has been multiplied and added to the first row. Why has this been done? Because this here we have a minus 4, we want to make this element 0. So we have done and made this element 0. Hmm. And then in this same problem, uh, we have done another operation where we have multiplied plus 7 into row 2. So here we are using row 2 because this row 2's form is very suitable for making the other rows 0. You could have chosen any other row for this purpose. So this is added to this row 3, so to make this particular element 0. And similarly, another row operation has been done, and to make this element 0. Now, our finding is that while we have done this row operation, this element has also become 0. So if we do the third operation that we have seen, and we like exchange this row 1 with row 2, then we will actually get our standard row echelon form. So this will become minus 1, minus 1, minus 1. This is 0, 5, 3, and 0, 0, 0. So here we see our lower triangle. This is 0. This is completely 0. And the diagonal and the upper triangle consists both 0 and non-zero elements. Now what we have to check here, we have to check how many non-zero rows are there. So the number of non-zero rows here are 2. So our rank is 2. So this is our answer. So we have converted into the row echelon form, and we have seen that the rank is 2. So I would like you to just do this problem for another matrix. So I will give you just two by two matrix, and this will be pretty easy one. So can you tell me what this is the rank of this matrix will be? So anyone can unmute and answer.
Maybe it will be one.
It will be one. That's correct. Hmm. So we what we can see here very clearly is that this row one, if we multiply it with minus two and add it to row two. So if we do this operation, row two transforms to row two minus two into row one. Hmm. We will see that this both the elements actually get vanished. Hmm. And also it can be very clearly seen that these two are not independent row vectors. So if I multiply it with minus 2, I am exactly getting this second vector. Sorry, this will be plus, right? Yeah. Hmm. So if I multiply this row 1 with minus 2, I will get this second row vector. So they are just related using a scalar. So its rank is, there is only one independent row vector here, so the rank is 1. Okay. If there is any questions, please feel free to ask.
Like, sir,
Yeah.
uh,
Yes.
we have that the rank is number of independent rows.
Yes.
So, like, if we see here, like, if we apply a operation that row, like, we can see obtain the relation also that row one is
Hmm.
equals to minus one by two into row two.
Yes.
So,
So let me.
like, there will be two dependencies.
Uh, can you tell me the row operation that you want to do? Row
Like, if
one?
we apply, like if we talk about the relation that row one can be obtained by dividing row two by minus two,
Yes. Yes. Sure.
and also we are saying that row one can be obtained by row two can be obtained by multiplying minus two
Yes.
the
That's
row one.
yes.
So
Hmm.
isn't this like two depend like we are obtaining the both the rows applying by applying some like
Hmm.
operation or something. So
Yes.
both
So
rows are dependent on each other.
they are dependent on each other. That's correct. But we have one independent. We will say that we have one independent row vector here because, like to get the other, we need one of them, right? So one of them will is independent, because we are not getting that from like we are given this. At least one of them needs to be given to find the other, right? We cannot like come up with both. And so rank should be at least one. Is
Okay.
my point clear? Yeah. So rank is at least one. Both are obviously dependent on each other, uh, but we will say it in this way that at least there is one independent vector. Otherwise, how did we get these row vectors in the first
Okay.
place? Yes. Okay. Is there any other question? Yeah, we can move to the next. So this is also matrix algebra itself. So we have to find the determinant of A inverse. Hmm. how should we proceed?
First,
Excuse me, sir.
for this, we can simply find the determinant of A itself,
Yes,
because
exactly.
on
Mhm,
taking the inverse,
mhm.
the determinant
Yes,
doesn't change.
yes, exactly. So to find determinant of A inverse, what we need to
Excuse me,
do is, yes, sure.
sir. This is classes of fluid mechanics or mathematics.
This is introduction to fluid mechanics. So we are solving the assignment 0 in this live session.
Okay, okay,
Okay.
okay.
Mm,
Thank you, sir.
yeah. Mm. So for finding this determinant of A inverse, we can simply find determinant of A, and 1 by determinant of A is determinant of A inverse. So uh, can you tell me what the answer is?
Sir, D 1/4.
1 by 4, that's correct. So this is pretty straightforward because like or we have three elements as 0, right? So we can find determinant by like going across any row or any column. Hmm. So we can choose this one for our simplicity because others are 0. So this is just simply 1 into this minor. So 4, 5, 0, 1. And again, this is pretty simple. Uh, 1 into, this is 4 into 1 minus 5 into 0, which is 0. So this is 4. So 4 is determinant of A. And determinant of A inverse is thus 1. Okay, so we move on. Okay, so here it is asked what is the lowest eigenvalue of the matrix. The matrix is given. So what is its lowest eigenvalue? So how do you proceed?
We do that equation A minus lambda I, and then we get a quadratic equation, and solving for quadratic equation, we get two roots of them,
Yes.
and the lowest
Hmm.
root is.
Yes. So its lowest is asked, so lowest will be. So here, so what we will do is basically to find the eigenvalue, we have to solve this equation as said. So we have to find this, equate this determinant to 0. So what, so this is a 2 cross 2 matrix. So we will get a quadratic equation. We'll do this. If you have any like question regarding this like solution of any of these problems, just let me know. Okay. So this will be is lambda minus 4 into lambda minus 3 minus 2 is equal to 0. Hmm. So lambda is has two roots. One is 5 and another one is 2. Right. So we can solve this quadratic. So the lowest eigenvalue is asked. Hmm. So can you tell me what is eigenvalue? What do you mean by eigenvalue? Hello. Yeah. Anyone you can say. Uh, yeah. So someone has typed in the chat vectors which do not get rotated by transformation. So what do you understand by that? Can you, like, you can say, like, you can speak up here. But we are not talking about vectors. We are talking about values. But I assume you are saying about eigenvectors. You can like say.
So basically, they are just scalars values that in a linear equation they are just scalar values
Hmm.
associated of when we make them just the quadratic equation when we make them in a matrix form, the
Hmm.
scalar
Hmm.
values. Yes.
Hmm. Hmm. So the eigenvalues are basically identities of this particular matrix in such a way that like matrices are used in previously also when we uh, like explaining the rank and all. So we stated that the matrix is mainly used for transformation of vectors. Hmm. So these eigenvalues, uh, they are the identities of this matrix in such a way that if the certain eigenvalues are associated with this matrix, they will give the same transformational properties. So this is related to this transformational properties of this of a matrix, and as stated by one of your friends. So like this is the eigenvectors are also like means eigenvectors are the vectors of this transformation which are actually do not get rotated when you apply this matrix on them. So they are rotating vectors, and from them we can find this eigenvalue. Okay. We can move. Okay, so now we will like come to a more closer field of mathematics related to the fluid mechanics. So we here we will discuss about the vectors. So you have, I think, two or three questions about on vectors as well in this assignment. So first one is divergence of the uh, uh, vector field. So you have to find the divergence of the vector field. So divergence, no, uh, we have this operator and dot product with this operator. This is our divergence. So what is this operator? This operator is nothing but partial derivative with uh, x I cap plus partial derivative with y j cap. Hmm. So we can write x y. We can here x y is written, or we can write x one x two as well. So as many dimensions are there. So here only two dimensions are there. So I'm writing up to this. So this operator is this, and we will just take dot product with this. So the dot product. hmm, So the dot product with this vector. So this is 2x2 cos y I cap plus sin y j cap. So, mm, so what is this partial derivative do? So first of all, we have to do this dot product. So dot product in dot product, I dot j or j dot I, these are zero. So we need not take those components, and I dot I is one. So we will take only multiply the only the same components. And here we will not multiply because this is an operator. So we will operate this del del x on the ith component. So this becomes del del x l- mm, del del x of e to power x cos y plus, and similarly we will do for the y component as well, del y over x sine y. Okay, so here since this is partial differentiation with respect to x, we will only differentiate the x terms and we will keep the y terms. Since y is independent of x, we will keep them. Y terms we will keep constant. So this will be simply e to the x cos y. And here similarly, this x term will not be differentiated, and only the y term will be differentiated. So what's the answer? We have this, right? So the can you tell me whether this can be a velocity field for a um, have you done in your in your lecture series is incompressible flows for, or continuity equations have you read so far? I don't know. Hello. Hmm. So okay, so can this be a velocity field for an incompressible flow? Why? So you can speak up, that will be more convenient for me. Why can this be not a velocity field? Okay, no problem. So why can this velocity field not be for a incompressible flow? Yeah, sure. Hmm. So for an incompressible flow, we need to have this zero. Hmm. Divergence of zero. Okay, so that's true. But here also, let's try to like understand. mm, Since let's try and see what this velocity field might look like. So we have, let me write it here. So we have e to power x cos y I cap plus sin y j cap. Hmm. So we have, if you try to visualize this velocity field, hmm, so I am drawing my axis here. Hmm. So e to the power x. So uh, e to the power x we know. So the value of e to the power x will keep on increasing as x increases, and here at 0 it will cross 1, and this is cos y and sin y. So suppose we want to find some this velocity field at some point. So let us say at 0 0. Hmm. At 0 comma 0 we want to find this velocity field. So what this will be? So at 0 0 this will be, this is 1, this is 1, right? Cos 0 is 1 and sin 0 is 0. So this will be I cap, right? So if I plot the velocity vector here at 0, this is a unit vector towards the x direction, right? So let's try and do this exercise. So can you tell me, uh, calculate and tell me for so why it is in sine and cos. So I will give some radian values here. So can you tell me for 1 comma 0 minus 1 comma 0 and 0 comma 5 by 2 and 0 comma minus 5 by 2. Can you tell me the velocity fields, like the value for this velocity? Yeah, so for 1 comma 0, what is the velocity? 1 comma 0, it is e comma e I cap, right? Minus 1 comma 0, this is similarly 1 by e I cap. What are the others? So 0 pi by 2, 0 pi by 2, this is j cap. So if we put here, so 0 pi by 2 is uh, j cap, and this is minus j cap, right? So we have just like this term, sine of minus pi by 2, right? So this is minus j cap. So let's plot this here. Okay, thanks for the help. So let's plot it here. So here this is 1 comma 0, right? Let's say this is 1 comma 0. So here we have uh, e I cap. Here we have 1 by e I cap. So all of them are pointed towards I cap direction, in the positive x direction, and you can see the velocity is increasing. So here we are trying to visualize if this had been a velocity field, say for example of a like fluid, then what it would have looked like. So it would have looked like this. If we see along the x-axis, it would have looked like this, that the velocity field is continuously increasing. So for any value on this x-axis we will have y equal to 0. So for any value on this x-axis, we would have actually got this with our x I cap. So here the velocity field is continuously increasing. Okay, now let's plot in the y direction what we have. Y direction, here this point is 0 comma pi by 2. Okay, here we have j cap, so it is in this direction, and here we have minus j cap. This is in this direction. Okay, okay. So here you can have a local idea about, and so to really have the whole picture about this velocity field, how we will see like means the fluid is moving and all, we will need to plot it for all x and y, right? But we cannot do that. That is not really possible. So if we even see in this little like domain, we can understand that how this cannot be a velocity field for an incompressible flow, because it looks very unrealistic that along the x-axis the velocity is continuously increasing, and also in this y direction the like some flow should go like this and here as well. So this does not look very realistic for an incompressible flow. This velocity field here looks as if it is diverging out of every point. Hmm. So here, like for example, if you see in this context of 0 comma 0, it is looking as if it is diverging out. Hmm. So that's actually what we mean by this divergence. So it has a very physical meaning. This divergence of a vector, this has a very physical meaning. When we are visualizing a flow field, or any field, any velocity field which does not have its divergence equal to zero, when you look at it, you will find that visually it feels as if like from a point the flow might be either diverging out if the divergence is positive, or converging in if the divergence is negative. Hmm. But for an incompressible flow, neither of this can happen because the density is constant and yes. The fluid cannot accumulate at a point or like come out of a point from nowhere. So a fluid flowing from some region needs to go to some other region. So we will never have this accumulating or diverging points in a velocity field for an incompressible fluid flow. That's why for an incompressible fluid flow, physically, like mathematically, you have already seen. Physically, this is a nice way to explain why of velocity field for an incompressible fluid flow, the divergence should be equal to zero, because there will be no fluid accumulation or fluid creation from any point.
So,
Okay. Yes.
if we just talk towards the left of origin,
Okay. Yeah.
so
Mhm.
we consider this, yes, this point.
Mhm.
So at this point, if we look that the velocity is only in one direction. So at this point, the fluid is incompressible, and
You need to actually plot the points adjacent to them also to have a field. So if you
okay,
plot here, you will find this is actually going more smaller, right? So if you plot at, for example, minus 2 comma 0, then you will have a slightly even smaller velocity field. It will be 1 by e square, right? 1 by e square I cap. So, but if you like go above here for example, so maybe at pi by 2, suppose that pi by 2, so this is minus 1 comma pi by 2, right? Hmm. So here also you will find that this is 1 by e 1 by e j cap, right? 1 by e j cap, I think. Hmm.
yes,
So here also you will find that the velocity is actually going this way. Hmm. At a very like this velocity vector is smaller than compared to the one at zero. So here also you will see that this is kind of like diverging out only. Hmm. And you can actually calculate how quantify this divergence if you just put the xy values here. So here we have calculated this, right? The divergence. So this is the divergence of this field, vector field. So this is actually a function of x and y. Correct. So each and every point in this physical space has a divergence associated with this vector field. Okay, am I clear?
yes,
Okay. So if you here put, for example, your point of concern minus 1 comma 0, then you will see that this is how much 2 2 by so this is a positive value. So fluid is as if it is getting created at that point if it were a fluid. So,
Yes,
uh,
yes.
hmm. So here, this is how we can like understand a fluid flow. So for a compressible perspective, these things can actually happen. That in a compressible fluid, these things can actually happen. That our divergence of the velocity field is not zero at all points. But for an incompressible flow, this will never happen. Okay. If there is in any other question, you can ask. Okay. So. mm, Hmm. I'll proceed. So here also like very similar question. So what we have to do is find curl. We have to find the curl of this. So if you know the definition of curl, you can easily find it out. So and you tell what the answer will be here, or how will you do it? So how will you do? I can show it here. You can do the calculation. So this is since this is a cross product, we will write it in this uh, determinant form. So we will write uh, here the cross product is between an operator and a vector. So we will first write the operator here. So instead of multiplying, we will just perform the operations. That's the difference between this and the normal determinant. So 2x square, 3z square, and y cube. So can you please calculate and tell me?
Sir, it will be a minus 3 I cap.
This will be uh, okay. Option A. Okay. So is everyone getting the same answer? So yeah, we can like see from here. Uh, so we are just performing a this cross product here. So we'll take this operator. This will be 3y square, and again this is 6z, and here we will not get anything because this del del z is operation is being performed on a function of x. So this is 0, and similarly del del x is performed on y, and here also similar. So only thing that is contributing is this first x component. So this is uh, yeah. So now we have to put the points, right? So everything is 1. So this is minus 3 I cap, as you said. Okay, so this is the mathematics of it. So like divergence, this also has a very a physical meaning. So can like someone try to say like the in the name curl, this meaning is there? Why is it called curl of a vector?
Maybe it's representing some rotation kind
Yes,
of thing.
yes. Hmm. So this is exactly this is rotation representing a rotation. Hmm. So when this is this we are getting this minus 3 I cap, hmm, at 1 comma 1 comma 1. So we can be sure that the field around this 1 comma 1 comma 1 will have some circular path. So suppose this is 1 comma 1 comma 1, and like out of this plane is x-axis. Hmm. So why I'm taking x-axis out of this plane? Because this is I cap. This rotation is I cap. So you can be very sure to find out that the velocity field just like surrounding it will have this some clockwise path. Hmm. So if you visualize it, you will find something like this. Hmm. Why clockwise? Because of this minus sign. If the x is sticking out of this plane, so this is sticking out. So this minus sign will ensure that this is clockwise, because right hand thumb rule basically. If you rotate your thumb around the direction of this, then it is in the negative direction. Hmm. Okay, so that is basically the physical meaning of this curve. So here also you have this x this mm, x y and z. So here you did not get this because it was given at a point, but you did get an expression for this velocity field. This is the expression for the curl of this velocity field. So this is a three-dimensional vector. So this has a distribution around all the three dimensions, but for every point you will get the curl as this. So what can you say about this velocity field? Here only the I cap component of the curl is there. So what can you say about this velocity field? If curl is only in the I, yes,
Rotation is about only one axis.
yes. Hmm. So rotation is about the x-axis, but it depends on which point you are in the YZ plane. Okay. Hmm. So where can you find such a thing? Rotation is about one axis, like any motion actually, which is kind of a like the velocity field. In the velocity field you can find the x component though. In the velocity field there is x component. So the velocity is varying in along the x direction, but the rotation is not there in the x direction. So something like, for example, if you have like a tornado or a cyclone, so the most of the rotation, it will be like perpendicular to the ground, and the other sides may not have, will have though, like it's not a perfect example, but will have very negligible this vorticity components compared to this. So it's not a very perfect example because it is very turbulent and there will be rotation components everywhere, but you can imagine your field in such a way that it's the rotation axis is mostly in the x direction, but your velocity field is varying. So these are two, not only with this divergence and curl is very helpful in like solving your problems, but it is also very helpful in visualizing any vector field that you are given. So if you get a velocity field, you by calculating its divergence and curl, you can understand a lot about how this field will behave. If the divergence was zero, then what? It won't have any
Impressive.
rotation. Yes. Mhm. So no solid body kind of rotation will be there. Hmm. Yeah. So this is also called as vorticity. If you, I don't know if you have like studied that in the lectures yet. Hmm. So this curl of velocity is also sometimes referred to as, means if this is a vector velocity field, then it is also referred to as vorticity. You can use this. You can use this. Whichever. Means many books use this. Many books use this. This is called vorticity. It will be covered in the lectures if it's not covered yet. Move to the next question. So again, very like mathematics based question. So this is like functions. So you have to find out whether this point has at x is equal to 0 if it has a minimum, maximum, or a point of inflection, or neither a maximum. So which one will it be?
It will be minimum, sir. A.
Hmm. It will be a minimum. Why? How did you know?
It tends to 0. The mod.
So tends to 0. What happens when this function is like x tends to 0? What happens to this function? You can say like you were saying. Who was speaking?
Yes, sir.
Yeah, yeah. So you can like say I didn't understand what you are saying.
Sir, from the
Hmm.
graph, the mod,
Hmm.
when we plot the mod graph, so
Hmm.
it give means minimum value at 0.
Yes, yes. Sure. We need to plot the graph here. Okay. Why do we need to plot the graph? Means there is another way of like finding a minima, right? So we like
We have to like
hmm,
take the derivative
yes,
uh,
exactly. Hmm.
of the function and
Yes,
then again take the derivative.
yes,
Then we
yes,
check the sign whether it is
yes.
negative or positive.
Correct, correct. So if I have a function f of x, if this derivative is 0, then it might be either minimum or maximum or point of inflection, right?
Yes,
Hmm.
yes,
And then if we take another derivative hmm, and put that point here. Hmm. So uh, if this is greater than 0, then this is a minimum. Hmm. That means the slope is changing direction. As you are increasing x, then the slope is becoming like this, then it's changing direction. So you will get a curve which has a minima here, a minimum point here, since this is changing direction. So you will get a minimum. Hmm.
yes, yes.
And then what happens if this is negative? If this is negative, then uh, you will have simply a
We may have
maximum. Mhm.
we will have like we will be sitting on the top of a crust, like
Yes, exactly. Hmm. And what if it is 0? Then what happens? Then
then we just
it is complicated. Then you have to calculate another derivative. Hmm. And there is a bunch of rules, but it is not very relevant here. Hmm. So this is how you will do it mathematically. Like, purely mathematically, this is how you will do. But here that is not required, and that is not possible as well. Why it is not possible? Because the point that it is asking, this function has no derivative. The derivative is not defined at that point, right?
yes, yes,
Hmm. So why is that not defined? Because this function is actually a piecewise function. This is defined piecewise. Piecewise means it has two definitions depending on which domain you are looking for. So this f of mod x is basically x only when x is greater than 0, or you can also write greater than equal to 0. And minus x when x is less than 0. Hmm. So this has actually two definitions, and x is equal to 0 lies exactly at the middle of these two definitions. So you cannot calculate a derivative. You may be able to, but like if you find out the left hand derivative and right hand derivative, and you will see that those two are not equal. So what is the method here? Exactly as we said, we need to plot the graph. So how can we do that? We can simply use these two definitions. Hmm. So if f of x is equal to x, that is pretty simple. Uh, so it will be a straight line. So x, x is the value, whatever the value of x is, f of x has the same value. So this is simply a straight line with a 45 degree slope. And similarly, this is only for x greater than or equal to 0. And for less than 0, this is minus x. So minus x, whatever the value of x is, the f of x has a negative value. So this is negative 1. So f of x will have plus 1 value. So it will be this side. Hmm. So it will be this side. So I'll just join all those points. We will again get a straight line. Here the slope is 3 pi by 4. So this is the angle. 3 pi by 4 if you are using all like straight lines conventions. Hmm. So we have simply this uh, V looking curve, and sure enough, at point x is equal to 0, this is the minimum. This is basically attaining its minimum at this point. Okay, it's pretty simple question. Here the graph is there. Okay. Any question? Okay, proceed to the next question. Yeah. So here they are asking to find the limit. So how to do this? How shall we proceed? So like any one of you can like, answer how can we proceed to find the limit. So we cannot find the limit straightforward by just putting the value here, because that would not be defined, right? If you put 0 here, the denominator becomes a 0 and the numerator is also 0. So it's a 0 by 0 form. So that one will not give any value. So we need to use some other technique to find it. So the answer is D. That's correct. But how to do it? How to proceed? Can proceed in many ways. Hmm. One is the very simple method is there is a rule called L'Hopital's rule. Hmm. So L'Hopital's rule, or in Indian pronunciation, L Hospital's rule. So this what we do here, if we have a 0 by 0 form, we simply take the derivative. And it's the rule, this rule is basically, if we have limit x tends to 0 f of x by g of x, and we are already given that limit x tends to 0 f of x is equal to limit x tends to 0 g of x is equal to 0, then this, if this is true, then this will be equal to limit x tends to 0 f dash x by g dash x. So this is a long definition, but basically what it means, whenever you see 0 by 0 form, then you have to take numerator derivative of the numerator excuse me, a derivative of the denominator. And then again put the value x is equal to 0 and see whether it is coming or not. Then you have to like take derivative again if it is not working. So here we already saw that it is 0 by 0. So if we just take derivative, then derivative of x is 1, derivative of 3x square is uh, x cube is 3x square, and this is basically cos x. Now what happens if we put 0? So this is 0, this is 0, this is 1, this is 1, so this is minus 1. So this is a very straightforward question, but actually we do this kind of things a lot in fluid mechanics. So here we see there are two terms, just term 1 and this is term 2. This vanished, but this was important. So our limiting value for the our limiting value, this term was the second term was actually that was important. So if I had some 2 here, this answer will change to -2, right? But if I had anything here, suppose if I had 4x cube, will the answer change? My answer will still be -1. Hmm. So, so my answer will be still be -1. Why? Why is this term not important as important compared to this? Because this is of the this has an order 3. So this has an order 3, and we are like x is suppose a very small, something very small, which we are like shrinking. And sin x is what? Sin x is of the order 1. Why of the order 1? Like if you do a Taylor expansion of this, sin x will be something ax minus some x cube by 3 factorial and a lot of other terms. But these cube terms will go to 0 faster compared to these linear terms. And that is the catch why this second term is more important than the first term. Hmm. So whenever we do like later in this fluid mechanics courses, we will do something called as order analysis, where we will judge. So there will be an equation. We will judge which terms are more important in such certain situations compared to the other terms. So this is a very classic case of this. So this looks like a very simple problem, but has this means uh, has this concept to it that this order 1 terms will actually disappear slower compared to this order 3 terms. For example, if you have something which is proportional to your volume, so some force, probably, let's say you have already studied about some body forces and surface forces. Hmm. So let's say we have some surface force, and that surface force is let's say S, and this is proportional to your area. So area, some length is there, so it will vary as some length square, and you have some volume force. So volume force, I'm like, it's body force. So body force, let me put body force as B. Hmm. So you have some body force, and this is a body force per unit volume. So this will be multiplied with some L cube. Now when you are making this smaller and smaller, when you are shrinking, when you are making L smaller, which one will dominate? This body force term will actually shrink faster, right? Because this is a cube and this is square. So this will shrink faster. So at your smaller L, this term becomes important. This term gains importance compared to the body force term. So that's what you will find in effects like capillary action and all. So or like if you for example, uh, like in water, if you just hold a piece of paper and just dip one edge of this paper to the water, you will see the water will rise. So that is a capillary action. So why is this water rising? This is rising due to a surface force called surface tension. Hmm. So you so learn about this in your courses. This is force. This is capillary force, which is drawing your fluid inside this paper. Hmm. Uh, so what is this overpowering? This is overpowering your gravity force. So gravity force, since the length between your fabric of the paper is very small, this L is very small. This term is becoming very small, and your surface force is actually winning, and thus your water can like rise above this paper. Okay, so can ask if there is any question on what I said. Was I clear?
Yes, sir.
Okay, okay, thank you.
Sir, I got the second term uh, that the why the water is rising, but how the gravity force, how the
Hmm.
rising force is dominating the gravity force, I didn't get
So,
it.
so the gravity force will be mass terms the gravitational acceleration, right?
Yes, sir.
So this is your gravity force, force due to gravity. Hmm. So this is basically your density into volume. So volume I can write some length scale. So for example, between those fabrics of paper, whatever the length is there, so write that length cube into g. So when your length is shrinking, so this is shrinking on in the order of 3, and
Got it.
yeah, okay. So this is basically how I was querying. Hmm. So gravity force and the surface tension force, those two forces are acting there, and the gravity is much smaller compared to the surface tension force. Okay, let's proceed. Okay, so this is just the solution. All right. So next we have another. This is a maths problem. Yeah, how will you solve this equation? Hmm. So this is a differential equation. First order differential equation. So you will need to integrate it once to get the solution. And one initial condition is given, so that you can get your the value of your integration constant. Hmm. So I I'm sure you have done it. So like let me uh, just do it with you. Hmm. So very nice thing about this equation is this right hand side is zero. So I can simply separate these two variables. So I have only two terms. So I can easily just separate these two variables. Hmm. Minus x cube dx. Yeah. So I will integrate this, and what I get here is uh, y to the power 4 by 4, hmm, x to the power 4 minus x to the power 4 by 4. I should have by 4 here, and an integration constant. Hmm. So you can write by 4 in both terms, or you can simply say my this term has engulfed this force, because if I just multiply by 4, I will get this equation. Hmm. Uh, so what condition is given? Condition is this. So if x is 0, my y value is 1. So I'll put x 0, y 1. So what I'm finding by what am I finding by this equation? I am trying to find c. So uh, this is 1, this is 0, and c. So my c is 1. So yeah, you can put minus 1. So what is the answer? You can put minus 1 instead of 1 instead of 0 in this equation. Find y. So what will be the value be?
Sir, it will be 0 C.
No, it will be 0, right? That's correct. Hmm. So C is 1. So my final equation stands as this what is this x to the 4 plus y to the power 4 is equal to 1. Hmm, right. So if x is minus 1, if did I write it correctly? Yeah. So if x is minus 1, then this is 1. 1 plus y to the power 4 is equal to 1. So y will be 0. It's very straightforward. Okay. Uh, so here we needed only one boundary condition. So what if this order would have been more, then we would have needed more boundary conditions, right? Because the integration constants would have been more. Okay. So let's just go to the next question. If there is any doubt, you can tell me. Okay. Yeah. So this is actually almost same question. So you have to again solve an equation. So how to proceed with this? Can we do the same thing as we did in the previous problem? Yeah, so we can do it in a similar way, right? So can you tell me what the solution will be? The solution is A. So you are in uh, C. You are saying no. Let's see. Let's do it.
Sir, it will be
Mhm.
B, sir, 2 e to the power minus x square. Yes, sir, B.
Okay. So I have got A. I have got B. I have got C. Let's see what it will be. So this is dy dx and minus 2x. So we can simply separate variables here. So there are only two terms. Easily we can do that. So dy by y is equal to minus 2x dx. We'll integrate both sides. What will this be? This will be
ln y.
yeah log. Yeah, we can write ln actually. That will be better. So ln mod y. So this is equal to what this will be minus x square, right?
Yes, sir.
So we can simply put it like this. E to power minus x square, right? Okay. So there was I I'm completely
Constant.
missing. Yeah. So there is one constant here. So this is e to the power plus c. So I can simply write a here. What do I mean by this? I mean e to the power c is equal to a. Okay. Is this step clear? So I would have got e to the power minus x square plus c, which I could have written as e to the power c into e to the power minus x square. So I am just writing e to the power c as a. Okay.
Okay.
You can put now x is equal to 0 and you are supposed to get 2. So if you put x is equal to 0, this is e to the power 0. So a is 2. Hmm. So a is equal to 2. So I am not getting any other term here. So I am not getting any other term. What I am getting is I am getting b. Hmm. So y is equal to 2 into e to the power minus x square. Okay. So this is one way to solve this problem, and I think it was meant a little bit differently as well. So like we can also do it in this way. So this is more useful when you have some other, like instead of 0 you have something else, some other function here. So this is what this is in the form of a linear equation. Why linear? Because y or y's derivatives, dy dx and whatever else terms we can have. So y and y's derivatives, their order is their power degree is 1 here. So this is a linear equation. So for a linear equation, we have an integrating factor. So what is integrating factor? Basically, something if we multiply and we can like reduce it to two terms. For example, let's like see in this general case only. So we have this dy dx plus py equal to q. I wrote it again. Yeah. So if we multiply something which can actually like reduce this first term, this has two terms here, so to one term, a perfect differential it is called. So what that would be? Hmm, so we are worried only about this portion. The second portion we can integrate. So we are worried about this portion. So let's say that we multiply e to the power hmm, uh, yeah. First of all, why we are choosing e to the power something? So, like that we are only like choosing such that this remains a linear function. So basically, if we do e to the power, we will take derivative. This will come out, and this e to the power thing will remain. Since because e to the power x derivative is e to the power x itself, so if it is e to the power some other function, that function will remain. So I can multiply this whole thing and still get a compact form. So we will see what I mean by that. So like let's just do it itself. If I take multiply this, then this is like this whole thing behaves as if this is into integration p dx y. Why? Because if I differentiate this, now you will see what I mean by when I said we need e2 or some function. Because uh, first, I am not differentiating this. I am differentiating y. So I need to differentiate one, then I need to differentiate the other term because these two are multiplied, right? So first I am differentiating y term. So this stays as it is, dy dx. And then I am differentiating the second term. So the y is there. So y is there. This gives me this like in a linear function we need to have this y. And since I am differentiating this, e to the power integration pdx will also be there. That's why multiplying this does not like means can assure me of this closed form. So this term remains. So I can safely multiply this in both the terms and get a closed form. And then I have to differentiate this integration PDF. Integration of differentiation of the integration is the function itself. So this is P. So I get this form. I get this form back. So instead of writing this first, this left hand side, I can simply write this and equate to whatever was there in our left hand side multiplied with this integration factor that we have introduced to solve this problem. Hmm. In this case, you actually don't need to do all these things, but in this case this is 0, so this term will be 0. So you just simply get e to the power integration p dx y into y is equal to some constant a. Hmm. Okay, if you take this the other side, then this is e to the power minus integration p dx. What is p? P is 2x. So integration 2x is uh, integration 2x is x square. So it's power minus x square. And we get the same thing as we did before. Okay. So, I think this was the last question. Yes. So thank you. If you have any doubt in this assignment, please ask me. Okay. And I heard that you are already in week 3, so this is lagging behind. But like this slot is given to me every week, so I need to like do the next. Means next week we will be doing the assignment 1. So the same time, same link, we will do the next assignment. Okay. Uh, and if you have any doubts from like that assignment or the topics related to that assignment, we can like solve it at that time. So you can like come to me with questions. We can address that. Okay.
Okay, sir.
Hmm. So like in this assignment, if you have, do you have any doubts or relate in the topics related to this assignment, which are basically preliminary, whatever knowledge is required before doing this course. So we are doing the prerequisites here. Okay. If not, we can end here.
Okay, sir.
Hmm. Okay.
Thank you,
Thanks
sir.
for thanks
Thank
for
you.
joining. Yeah.
Sir, your way of explanation is very nice.
Oh, thank you so much. Thanks. I'm ending the session. Okay.
Okay, sir. Thank you, sir.